Okay, today we derived the Euler equation, and the Euler equation describes pressure variations in a fluid that's undergoing an acceleration. So the way we derived it was to consider a case of a volume of fluid that's accelerating in the L direction, and the result of the force balance on that volume is that d by dl of p plus gamma z is equal to rho times the acceleration in that direction. Note that we have two locations where we are defining the direction L. We converted those into x and z directions in class, and what we found was that minus d by dx of pressure is equal to rho ax, because dz dx is 0. And we found that minus the pressure gradient in the vertical is equal to rho g plus rho ax. Now, if I just start back from the Euler equation and manipulate it a little bit, suppose that I say that AL equals 0. So we have no accelerations. I'm not assuming the fluid's static. I'm just saying there are no accelerations. In that case, we can say that minus d by dl of p plus gamma z is equal to 0, or dp dl is equal to minus gamma dz dl. And from this we can say that if L is the x direction, we can say that dp dx is equal to 0. But if L is the z direction, then we can say that dp dz is equal to minus gamma. And so these are the hydrostatic relationships, and what they depend on is simply the assumption of no accelerations. So we have no accelerations, and therefore we can conclude that the hydrostatic pressure distributions hold. More generally, we have these two equations. I just noticed that I made a mistake over here. This should be a sub z. Okay, note in the earlier part there, I had that a sub x. It should be a sub z for the vertical component. Okay, finally, the examples that we did in class involved one case of a linear acceleration. That was the case of the tank sitting on top of my car, and one of a radial acceleration. And for that, I should note that for solid body rotation, just by definition, I had a couple questions about this at the end of lecture, a sub r is minus r times the angular velocity squared. And that is just the definition of the radial acceleration that's required to maintain that solid body rotation. Okay, so the basic result here, let me just emphasize it, is the Euler equation, and for the L direction is given by this equation at the top. It's the one that becomes the basis of the integration that we'll do to define the Bernoulli equation next week. It is also the simplification of our later differential momentum conservation descriptions for the case of, I guess, steady flow, and it doesn't have to be steady accelerations perhaps, and no viscous forces. So, all right, have a good weekend.